Okay, so in this section, we'll not go over derivation because we already know this result from dynamics. Just I want to highlight that the velocity vector in streamline coordinates will be along S, because you know by definition that the streamline is the line for which velocity vectors are tangent at any point. So if I want to determine the velocity vector at any location, this vector will be tangent to the path. So it will be along what we call in general in dynamics UT vector, tangential unit vector UT, or here we call it unit vector of the streamline, along the streamline, which can be called S also. So the velocity vector is always along UT, because UT by definition is defined as the unit vector of the velocity. So if you remember from dynamics, when you defined UT-UN frame, UT is always following the velocity, it's its unit vector, and UN represent what is called the normal coordinates. So if you remember, this type of coordinates UN UT is called normal tangential frame. Okay, and the characteristic of this frame is that it constitutes the plane of motion at any instant, and therefore I can consider that instantaneously my particle is moving in plane UT-UN. And the acceleration can be expressed in this system function of both directions. So we can demonstrate that the acceleration vector will have one component along S, which we are used to name as AT in dynamics. AT is the tangential acceleration, and it represents the change in speed, dv by dt. So if you have change in speed, then you have tangential acceleration. If you are moving with uniform velocity, then you have zero tangential acceleration. On the other hand, whenever you have curved motion, automatically this will induce a component of acceleration along UN, because AN is the component of acceleration that will allow you to change direction. If you cannot change direction without having a normal acceleration. And in dynamics also, you have demonstrated that AN is V squared over rho, where rho represents the radius of curvature at any location. So if I want to illustrate it for you in this figure, for example, at this point, you can consider that when moving over this segment, I am like moving on a circle, on this circle at this instant, and I can define at this location a certain radius, rho 1, okay? So this is at point 1. If I consider another point here, point 2, if I find here this segment will be part of another circle of radius, rho 2. This is what we call the radius of curvature. And at each location in a curved motion, we have a new circle and a new radius of curvature. Okay, so at each location, to determine the normal acceleration, I need to know what is the velocity at this point, and I can determine the normal acceleration as v squared over rho. So in summary, the acceleration vector can be written as, can be decomposed into two components, which are the streamwise acceleration and the normal acceleration. Okay. Now we will define a very important concept that we will use in next chapter, in the whole chapter, as application. So now we'll develop together what is called the Reynolds transport theorem, and this general theorem will be the main theorem that will be used in next chapter, and will be applied to come up with the different conservation laws in fluids. So we will derive together the continuity equation, which is related to conservation of mass. We'll derive together the linear momentum equation, which is similar to Newton law in dynamics. We'll derive together the energy equation, which represent, for example, one particular case of this will be the Bernoulli equation, which represent conservation of mechanical energy. So all these laws for which will describe fluid behavior will be based on one theorem, which we will derive together now. Okay? To be able to derive this theorem, we need to go over some concepts in fluids. The first one is the difference between a control volume and a system. Okay? The main difference between a control volume and a system is that a system is a collection of matter of fixed identity. What do we mean by this? So we are always tracking the same atoms, the same molecules of fluids, and we follow them as they move in space. So for a system, if I want to write the definition of a system physically, I can say that I am considering the same mass of particles. Okay, so m is constant. I cannot have, for when I consider a system, the mass cannot change because I consider certain particles. Let's say, consider for example flow over a pipe. Let's say I am interested in particles in this part in particles occupying this volume at a certain time. If I follow with time what will happen with these particles, they will move through the pipe system. So with time I can track all my particles and determine their new locations. So I will always follow the same particles. This is why the mass of the system will not change, because I'm always observing the same fluid particles. On the other hand, for the control volume, this is completely different. For the control volume, I am interested in a certain region of the space. And in this region of space, I can have modification of particles. Some particles will enter, other will exit. So, for example, if I consider the same example, I can just observe if you want, one region of my duct. So I say I am interested at what is happening in this region of the duct. So some particles will come inside, others will get out. Okay, so I have continuous change of particles in this case. I might have, if I take I can have unsteady problems, so I can have accumulation. Let's say if you take a reservoir, if you are interested as control volume into this space, this reservoir, with time, and you have a flow of water entering your system. So with time, the fluids, the particles will take place in the reservoir, and the mass inside the reservoir is changing with time. So in this case, the mass is changing in my control volume. So to summarize again, for the system, it's a collection of matter of fixed identity where always the same atoms or fluid particles are moving, and we are observing them, and we can see how they interact with their surroundings. But this interaction will include, if you want, fluxes of energy, fluxes of momentum, but will not include fluxes of mass. For a system, I consider the mass as constant. I don't have any new particles coming in or any particles getting out. I can have these particles can exchange with the surrounding energy, can exchange different variables, but it cannot exchange mass. Okay? So, while for the control volume, we just consider a certain volume in space or geometric entity that is independent of the mass through which fluid may flow. So we have new particles that can enter this control volume while others will leave it. Okay. Now, for both system and control volume, they can have variable geometry. And what do I mean by this? If I give you the example of the balloon control volume, if I'm interested in as a control volume in a balloon, this balloon can change in volume. So if I have, let's say, gas that will enter it, it can expand it. So the geometry of my control volume can be variable with time. And the same for my system, because whenever you have compressible fluid, you might have change in volume while the mass can remain the same. Okay, so for both system and control volume, you can have change of the geometry with time, but the basic is that for the system, the mass will remain the same. I'm exploring not just the mass will remain the same, it's same mass and same particles. While for the control volume, I'm considering a certain space of interest, and I will see what is coming in and what is getting out of this space. Okay, now it is very important to relate these two concepts. We'll see why. Because in fluids, we are interested in both systems and control volumes. And by relating their properties, we'll be able to define all conservation laws, which will determine the behavior of a fluid. Okay? So to start with, to be able to understand how we will link uh, variables of a system to the variables of a control volume, we should keep in mind that we have two main approaches of analysis for fluids that we already discussed together, the Lagrangian approach and the Eulerian approach. So if you go back to the definition of system and control volume, you can see that for the system, I am nearly working with the Lagrangian approach. Why? Because I'm following the mass. So for the system, I have the same particles that I follow. So when we talk about system, this is Lagrangian. While when we talk about control volume, this is Eulerian, because for the Eulerian approach, if you remember, I take a certain flow field and I observe it. Some particles will come in, other will get out. I'm always interested in the same zone. So when my this approach to describe the fluid behavior is to consider a certain space and observe what is happening at each location, this is an Eulerian approach. While if I consider that to describe the flow, I will take a certain particle and follow it with time, this is Lagrangian. Now, both techniques are interesting and they can give me an idea about the flow behavior. And we'll see together that the Reynolds transport theorem will combine these two approaches into one equation. Let's see how. So mainly, what is the problem that we have? That the laws of physics, in their simplest forms, describe systems. And if you remember in dynamics, what do? To find a relation between velocity and acceleration, you consider a particle, you follow it, you say that A is dv by dt. So I can follow the particle with time to define its position, velocity, acceleration, etc. So Newton law that we are used to use in general was applied as a Lagrangian approach on a certain particle that is followed. Okay. Now, the problem in fluids that it is impossible to keep track of the system in many fluid problems. In fluid problems, it's easier for us to explore what is happening in a certain region of space. This is why we need to that all physics laws that we know already should still hold in Eulerian word. So I know, let's say Newton law, sum of forces equal ma, which consists on tracking a particle with time. So let me also try to link the Lagrangian and Eulerian approach in an equation. This is to bridge this gap. We'll think about the Reynolds transport theorem, which will relate the properties of a system, which is the concept of Lagrangian approach, and the properties of a control volume, which is used for Eulerian approach. So Reynolds transport theorem will be a moving system that is flowing through a control volume. This is the whole idea. And I want to try to relate the properties of the system and the control volume. Now, in order to understand this theorem, I will just first describe it, and I will give you a 2D example to understand each term represents what. Okay? So first I will state what the control volume conservation equation represents. So first, this is a general theorem that can be applied to any property of the system. When we talk about property, it can be, we'll see that it can be velocity, it can be energy, it can be any property related to the fluid behavior. Okay, so we say that the way of describing properties is when you use a capital letter, then you are giving the total amount of a property in the system. While when you give it as a small letter, then you are considering the property per unit mass. Okay, so per kilogram. Now, what the Reynolds transport theorem will tell? The Reynolds transport theorem will tell me that if I consider a system and I want to find what is the variation of a property in the system, okay, I should first find how the property is varying in the control volume, plus I should account for fluxes that will cross in and out my control volume. So now this is in brief what the Reynolds transport theorem is. You will not understand this equation before we take a simple example, okay? But just keep in mind, this term, the first term, represents the rate of increase of a certain property in the system. This term represents the rate of increase of the property in the control volume, while the final term represents the rate of fluxes of the property across the control volume boundary. In order to simplify this approach more, so you can consider that any system, okay, will consider certain mass of particles and will follow it. So imagine that you have some particles and you want to follow that. What the difference between control volume and control system is that the control volume will only take a certain part in space and observe it, while the control system will follow the particles. So if I consider at a certain instant that for a certain time t, the system and control volume are in the same position, okay? What will happen is that after a certain time, so if this is the figure at time t, okay, I consider this is section 1, this is section 2. I consider that the system I am interested in is the particles between 1 and 2. And the control volume I am interested in is the geometry zone between sections 1 and 2. So at the first instant, they were coincident. So at time t, I can say that the control volume was occupying it was the same material. The material of the control volume was exactly the same of the system. Now, after a certain time, this will not be true anymore. Why? Why? Because let's say you have a flow, some of these particles will get out, and some other particle will progress in the fluid zone. Okay, so now if I want to represent at another time t plus dt, my system and control volume, the control volume will remain in its place. If I'm considering here, I am interested in this zone in space between 1 and 2. Okay, so for the control volume, it will remain in the same location in this example. Not always, we'll see that it can be moving, but in this example, it will remain in this place, while the system will occupy a new place. So I will draw it dashed. So my system will occupy a new place because some particles will leave the control volume and the other will move inside. Okay. So from this observation, I can just say that to link the variation of the property in the system to the variation of the property in the control volume. I need to know what fluxes of mass are coming in and getting out of my control volume. Okay, so this is why we say that this term will represent the fluxes through the boundaries of my control volume. So here you have a flux coming in, and here you have a flux getting out, and due to these fluxes we'll have differences between the system and the control volume. So this is an overall approach to understand what the Reynolds transport theorem represents. Okay, now I will try to give you a 2D example to illustrate this to illustrate the different terms of this equation. Okay, any question before we continue? Okay. So let us take before doing examples, I want you to consider this 2D example. Okay, so in this 2D example we have a nozzle, and as we said before, we need to try to relate properties of a system and the control volume. Okay, so let's say you have a nozzle and you have a flow through this nozzle, and you want to characterize the flow behavior. Okay, now you will say, I am interested in the flow field within my nozzle. So my control volume will be the nozzle, let's say. Okay, so my control volume is the nozzle. Now my control system will be some particles that at a certain instant were inside the nozzle, but if I want to follow them with time, they will not always remain inside it. So, for example, I can consider that at a certain time t, my nozzle is full of particles. Okay, so let me define at this instant t my control system as the fluid particles inside the nozzle at time t, and my control volume is bounded by the nozzle inlet and out. Okay, so if my nozzle is fixed and I have a flow of particles over it, then at any time t, my control volume will be limited in this example by the same geometry. Okay, while my control system will be moving. Okay, I repeat again, this is a particular case. We'll see after that in some cases the control volume can be moving, and we'll see then what to do. Okay, but now just since the theorem is already complex, we don't want to complicate everything from the first time, so we'll give a simple example to understand the concept, and after we'll go over more particular cases. Okay, so as you can see here, the line in blue represents the fixed control surface and system boundary at time t. So at an initial time t, I considered that everything inside my nozzle is my system, and I want to follow it. Okay, so at time t plus dt, since my nozzle is fixed, my control volume will remain at its place. So the blue boundary will still represent the control volume surface at time both t and t plus dt, while my control system will change in location because my fluid particles are moving. So the particles that were at this level will move to a new level here, and the particles that were at section 2 will move out of the nozzle. So the black line, okay, will represent the new position of my control system at time t plus delta t. And my purpose is to try to relate the control volume and control system. Okay, how can I do this? If I observe my figure, I can say that at the first instant t, the system was equal to the control volume. Okay, while at time t plus dt, my system is now formed by this geometry, this one. Okay, this geometry represents what? If I want to express it function of my control volume, it is equal to this part minus, so this is what this is. This is the control volume. Okay, I should subtract from it part 1 and add to it part 2 to obtain the new position, the new system. Okay, so my system can be written at time t plus delta t as the control volume minus area 1 plus area 2. If you want, area 1 will demonstrate that area 1 represents the flux coming in, and area 2 represents the flux of mass or the flux of property getting out. This is why we can say that the rate of change in the system is equal to the rate of change in the control volume plus fluxes crossing the control surface. Okay, now let us demonstrate together that these areas 1 and 2 represent fluxes. Okay, look, if you want to consider this part, this area is equal to what? It's equal to this distance, okay, times this one. Now this distance is the distance moved by the particles between t and t plus dt. Okay, the distance moved by particles between these two times can be calculated simply as the velocity of the particles at section 1 times delta t, because we are considering a very small time step, while the distance moved at section 2 here, delta L2, is the velocity of particles at section 2 times delta t. Okay, so now we'll use these distances to try to express, if you want, the difference, to show that this is related to a flow rate. What is the area 1 and area 2 are related to flow rates coming in and getting out of our control volume. Okay, so let us write together. Until now, what did we do? We said that at time t, the system and the control volume were occupying the same place. This is why the property of the system at time t is equal to the property of the control volume at time t. Okay, now the system at t plus dt is different. We have seen together that it's equal to the property of the control volume minus the property in part 1 plus the property in part 2. Okay, now if you remember, what I am interested in is to link the variation of the property of a system to the variation of the property in the control volume. Okay, how I define the variation of property in a system? The rate of variation of a property with respect to time can be written as the property of the system at t plus dt minus the property of system at time t over the time step delta t. Okay, now I will replace the expression of the system at t plus delta t by its expression. So I will replace it by property of the control volume at t plus delta t minus property of part 1 at t plus delta t plus property of part 2 at t plus delta t. And now, using that the property of the system at time t is equal to the property of the control volume at time t, I can replace this part by B control volume at time t. Okay, so what can I deduce now? If you take this term with this one, this represents B control volume at t plus delta t minus B control volume at t over delta t represents the rate of change of the property within the control volume. Okay, so what can I deduce? I can deduce that until now we have demonstrated that the variation of the property in the system is equal to the variation of the property in the control volume. And I have